Okay, let's start. Any questions from the previous classes? From the previous topics? Moving on. Okay. So, last time we formulated this theorem, intermediate-value theorem, but we didn't prove it. So, I repeat. Theorem: if a function that is continuous on a closed interval assumes values with different signs at the endpoints of this interval, then there is a point on the interval where it assumes the value 0. Okay, let's look at the proof. So I'm going to add a picture here. The picture will not be an important part of the proof. This is just an illustration. So we have an interval from a to b, and to a function looks something like this. So let's divide the interval. Let's call this interval A1, B1. In half. So let's take this point C, C equals A1 plus B1 divided by 2. If f of c equals 0, then we have found the point in question. The theorem says that there is a point where the function assumes 0, and we have already found it. Then this is good. Then we have found the point. So this would be a very nice thing. But perhaps it isn't. If f of c is not 0, then the function of x must assume values with different signs at the endpoints of one of those intervals, either from A1 to C or from C to B1. Well, you can easily see this. if the value at this middle point is negative, then we take the right half of the interval. If it's positive, then we will take the left side. Means of one of the intervals from A1 to C or from C to B1. So my function assumes assume values with different signs at the endpoints of one of those intervals. Let's call this interval A2, B2. In this interval, we proceed as we did with the interval A1, B1. That is, we divide it in half. And continue the process. So, looking at my picture, for my function, on the first step, I took this right half of the interval. So, since at this point the value is negative, the value the function assumes is negative, then I took this right half of this interval. Then for this next interval from A2 to B2, I do the same. I take this middle point, and I also look at the value at this point. In my case, it's positive, so I take the left half, and so on and so on. Once again, divide it in two, and so on. Then, either at some point, at some step, we find a point C such that f of C equals 0. Perhaps after several steps we hit this point. This could happen. But in this case we have found the point in question. Or we construct a nested sequence of closed intervals AN, BN. Such that at n points of each of those intervals, our function assumes different values with different signs. And also, since on each step we take only 1/2 of the previous interval, then the lengths of those intervals tend to 0. Because the length of nth interval is just the length of this original interval from A1 to B1 divided by 2 power n minus 1. Let's write it down also. Okay. Now, by the nested intervals theorem, there exists a unique point what should we call it? Guys, let's rename those middle points a bit. So in the first half of the proof, let's call this point the middle point in the first interval. Let's call it C1. So this would be C1. And then this would be from A1 to C1. This one let's call Cn. That's tends to 0. That not tends to 0. Okay. Okay, that's all. That's all. So the middle point of nth interval would be called Cn. Because I want to call this point C from the interval AB. Common. Хватит. Откройте, пожалуйста, дверь. Reconstruction. There exist two sequences. AN and BN. Those are the endpoints of our intervals. Two sequences. Such that either for any n f of an is less than 0 and f of bn is greater than 0, or for any n f of an is greater than 0, f of is less than 0. Without loss of generality, let's assume the first case. Any n is less than 0, f of bn is greater than 0. A proof for the second case would be similar. So this is the case that that I draw on the picture before, over here. So on the left points we have negative values, and the right points we have positive values. Okay. Good enough. Also, we note limit of an as n tends to infinity equals limit of bn as n tends to infinity equals this value c. So let me draw once again a picture. So on each step, we construct a smaller interval. So on each step, either left side of the interval grows, or the right side like gets smaller. So we have a n. So it gets smaller, 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 smaller. And there is a common point. So since the lengths of those intervals tend to 0, then the sequence, the increasing sequence of the left sides of those intervals has a limit, and the decreasing sequence of the right sides of those intervals also has a limit, and both those limits equal to the common point C, this point C. Okay, moving on. I of course meant that those sequences are not strictly increasing and decreasing. They are this is non-decreasing and that one is not non-increasing. Okay, so by the Heine definition of continuity of the function at point C and by the properties of limits we get that there exists a limit of f of an as n tends to infinity, and this limit should be f of c. Look, an is a sequence converging to this point C. So let's write down Heine definition of the limit of this function. Note that in this case we don't need this sequence an to be a Heine sequence. Think about it a bit. Think why we do not need it. It should converge to C, but it doesn't really matter if it equals to C. It doesn't equal to C in my case, but think about this anyway. So, since my function is continuous at point C, then this limit of f of an should be f of c. This is just by continuity. Also, since we know this bit, we can write down that this is greater or equal than 0, this bit. since those values are all negative, then the limit of those values should be, no, the other way around. Less or equal than 0. So a limit of negative numbers, of sequence that only attain negative numbers, should be negative or possibly 0. And also, similarly, we have the limit as n tends to infinity, f of bn. Similarly, it should be f of c. And similarly, we have that this should be greater or equal than 0. So, from those two statements obviously follow then f of c equals to 0. And thus we have found a point in my interval where my function attains value 0. End of proof. Any questions? Any questions? Corollary. If a function f of x is, no, not is, continuous on a closed interval ab, attains values f of a equals capital A and f of b equals capital B, then for any capital C between capital A and capital there exists a point small c from my interval from A to B, at which, no, not this which, not this which, at which f of small c equals capital C. Proof. Let's just apply the Bolzano-Cauchy theorem to a function g of x equals f of x minus capital C. Let's make it more capital. To expand on this a bit, since function f was continuous, then this new function is also continuous. Since C was between A and B, this construction means I don't care whether A is greater than B or the other way around, but it's still one of them is greater and C is between of them, is in between of them. So this function assumes positive value at one of the endpoints and negative value at the other endpoint. So we can apply the previous theorem and we will have a point where this function g attains value 0. That means f attains value c. Okay, any questions?
So if f of x less than 0 in any case, if we will start c, it will be less than 0, so we won't have points greater than 0.
So if f of x is always negative, then those two values are also negative, a and b, capital A and capital B. So this value c that is between them should also be negative. F, well, not f, g of small a, that would be f of small a minus c, that would be a minus c, and g of small b, that would be f of b minus capital C, that would be capital B minus capital C. Those two values should have different signs. So yes, though all of those letters independently could be, for example, negative, but still one of those is positive, one of is negative. For example, could be that way, maybe the other way. So no, everything works fine. Any more questions? Guys from Zoom, do you have any questions? So, no questions, moving on. Note. This is basically a reminder of a fact that we discussed during seminars, but I think I didn't discuss it during the lectures. For any subsequence x and k, the indices of this subsequence n, k are always greater or equal than k for any k. I will briefly remind you how we proved it. So we know that the sequence nk is increasing. Is increasing sequence of natural numbers. For k equals 1, this is true, and 1 is greater or equal than 1, since it's a natural number. And let for some value k and k be greater or equal than k, then n k plus 1, which is being strictly greater than k, and also be a natural number, should be greater or equal than nk plus 1. Follows nk plus 1 is greater or equal than nk plus 1. Since those are natural numbers. Nk is greater or equal than k, and we have plus 1. So, by mathematical induction, we have this statement. Okay, moving on. Any questions? Oh, we should take a break. Guys, let's take a break. 5-minute break. Wirstrasse. I should probably write it cleaner. Wirstrasse, maximum value theorem. It has two parts. Part A. A function that is continuous on a closed interval. Is bound on this interval. So any function that is continuous on a closed interval is bounded on this interval. And part B, moreover, there is a point on this interval where the function assumes its maximal value and a point where it assumes its minimal value. So, any function that is continuous on a closed interval is bounded and it reaches its bounds, its exact upper bound and its exact lower bound, hence making it a maximal and minimal values. Okay? Proof. Let's start with proving the first half of this theorem. Let's assume that a function f of x is continuous on a closed interval AB but is not bounded above on that interval. So, suppose we have a function that is continuous but not bounded above. Since this function is not bounded above, then for any natural number n, there exists a point, I will call it x, depending on n, such that f of xn is greater than n. Basically, I'm saying that here that this number n is not an upper bound for my function. There exists a point where my function assumes a bigger value. Very well. Very well. Okay. Now, those numbers xn make a sequence. This sequence xn, maybe I should write it over here. Let me write it over here. Oh no, I won't. Is bounded by A and B. Shoot. So there exists a number xn from my interval, of course, from interval from A to B, like that. So any number is greater or equal than n and less or equal than b. So this sequence is bounded. Okay, seems reasonable. Moving on. So we have a sequence that is bounded from above and below, so it has a convergent subsequence. Let's call it x and k. Convergent subsequence. Let the limit of this subsequence as k tends to infinity be number c. This is from interval A to B. Now, for any n natural number, we know that f of x, no, the other way around, the other way around. For any k, we know that f of x and k is greater than nk, because this is the way we have constructed this sequence xn. F of xn is greater than n. So if we put nk instead of n, we have this statement. Also, we know that for any k, it is true that nk is greater or equal than k, by the note that we discussed just before this theorem. Hence, for any k, f of x and k is greater or equal than k. Actually, strictly greater. Strictly greater. Because over here we have strictly greater sign. This bit was strictly greater. This was strictly greater. Okay, very well. Very well. Now, let's once again write the definition of continuity of my function at this point C and use Heini's definition of the limit. Once again, we do not need this sequence there to be a Heini sequence. this is a definition of continuity. So the sequence can like visit this value C. Hence, by Keynes' definition of continuity of my function f at point C, we have that there should be a limit as k tends to infinity of f of x and k, and this limit should be f of c. So this sequence tends to c by continuity of my function. F of those numbers should tend to f of c. On the other hand, since f of x and k is greater than k, it should follow that the limit of f of x and k as k tends to infinity should be greater or equal than the limit of just k as k tends to infinity, which is plus infinity. So those numbers tend to infinity, but on the other hand, they should tend to f of c. Contradiction. So f of c, let's emphasize that this should be a real number. Contradiction. Hence, my function is bounded above. Similarly, it is bounded below. So my function is bounded above and bounded below, so we have proved the first half of this theorem. Any questions so far? Покажите, пожалуйста, этот самый чат. Ну, ладно. Any questions? Moving on. Moving on. Now I want to prove that my function reaches its maximum and minimal values. So I'm proving the second part of this theorem. Since my function is bounded above,
there should be a supremum of my function as x is from this interval to be. Let's call this supremum capital M. This is a real number. Suppose my function does not attain this value. Any questions?
Is that a contradiction? Like the maximum value of a function is the higher value that it will attain. So obviously it will attain that.
No. We don't know that the function has a maximum value. For example, if we look at a function f of x equals just x on the whole number line, it doesn't have a maximum value. And also we can construct similarly like different examples. Let's for example look at a function f of x equals x on an open interval. So for example, on an open interval from 0 to 1. It doesn't attain either 0 or 1. So yeah. So suppose it doesn't attain M. Then for any x from AB, f of x is strictly less than capital M. Maybe this is the case. Which is exactly the same as to say that M minus f of x is positive. Then the continuous function M minus f of x is nowhere 0, but assumes values arbitrary close to 0. From the definition of supremum, my function f should assume values arbitrarily close to this capital M. So this function should assume values arbitrarily close to 0. Very well. It follows then that the function, let's call it g of x. This is 1 over m minus f of x. Is on one hand continuous, on an interval AB, but on the other hand, is not bounded above. So, this function, since denominator does not turn to 0, so this is a well-defined function. And by the same reason, since both functions in the numerator and denominator are continuous and denominator doesn't tend to 0, this function is continuous, just following from the properties of limits. So this function is continuous, but since the denominator attains values arbitrarily close to 0, so this function, 1 over this value, is not bounded above, arbitrarily large values attains. Okay, but this is a contradiction to the first half of the theorem. We have a continuous on a closed interval function that is not bounded above. This is a contradiction. Contradiction. Hence, my function f does assume value capital M. Similarly, it assumes the value small m, that is the infimum of my function on this interval. So it assumes both exact upper and exact lower bound. So those are maximum and minimum. So this is the end of the proof. Any questions? Any questions?
What's on the infimum there?
X is from the closed interval from A to B. Покажите мне на этот самый. Let me write it again. x is from a closed interval from a to b. Не знаю ничего. Ладно. Ну, хорошо. Okay, guys, any questions? Just to like construct this this contradiction. So I want to this is one of the ways to prove it. This is of course not the only way. So by taking this function 1 over m minus f, we have a continuous but not bounded above function. There are of course different proofs. Okay, any more questions? Okay, corollary. Let a function f be continuous on a closed interval from a to b. Let also capital M be supremum of f and small m be infimum of f. Then f of AB is a closed interval from M to M. I think I didn't use this, or maybe I did, this notation before. So if I take f of a set, I mean to construct a combination, like union of all the values that my function assumes at any point of this set. Once again?
Which one is the set?
This set from A to B. For example, in my case, this is an interval from A to B. So basically, this means a set of all values that my function assumes on this closed interval AB. And my statement is that this set of values is exactly a closed interval from small m to capital M. I think the proof is obvious enough, but I will explain it a bit. So we know that my function being continuous on a closed interval assumes values small m and capital M. And we know from the corollary to the previous theorem that it assumes all values in between those values. So it attains like exactly its maximum, exactly its minimum, and all values in between. So this is exactly this closed interval. Any questions? Any questions? theorem. The inverse function theorem. A function f that acts from x into R that is strictly monotonic on X subset of R has an inverse we'll call it f minus first power. This is not 1 divided by f, this is the inverse function, like sine and arcsine, or square root of, let's not use square root, cubic root and x power 3, the inverse function, that acts from y to x defined on the set capital Y. This is exactly f of x, a set of all values of f. So, a strictly monotonic function has an inverse function. To be clear, the inverse function is such that for any x from capital X, it follows that f minus first of f of x equals x. Is this enough? No, it's not. Oh, wait. I think this will be enough. Yeah, this will be enough. The function f minus first, so this is the inverse function, is also strictly monotonic and has the same type of monotonicity. As function f. So if function f, my original function, was, for example, increasing, then the inverse function would also be increasing. If condition. This value, this set capital X is a closed interval from A to B. And my function f is continuous on this interval x. Then the set y is a closed interval with endpoints f of A and f of B. And the function, the inverse function, is continuous on it. So, this last bit I think is easy enough to see. Well, actually all of it is easy enough to see. So I'm not going to prove it without proof. Well, I'm not going to rigorously prove it. I will briefly explain why this should be the case. So, if a function is strictly monotonic, then for bigger values of the argument, for example, we have a bigger values of the function. If we try to solve the corresponding equation, f of x equals y, we will always have exactly one solution. This solution is this inverse function f minus 1. It also would be strictly monotonic. For greater values of y, we will have greater values of x. If capital X is a closed interval, then by the previously proved corollary, and f is continuous on x, then the set of values is a closed interval. We said that it was from small m to capital M, from minimum to maximum. Here, minimum and maximum for a monotonic function would be f of A and f of B. I don't know which is the order, but those two values. And the inverse function is continuous on it. This part, I think, needs more explanations, more proofs, but we will skip the proof for now. Okay, any questions? Any questions? Okay, thank you for your time until I think 10th of January.